Hi everybody, Doc here. We're going to start our calculus class today with our very first lesson, Lesson 1, Chapter 1, Section 1. I'm going to attempt to use a pen because it's a little darker and easier to see on the video. We'll see how that goes. And this class is going to be a pretty fast-paced class, but the good news is you can rewind and go back through your video. If you are actually signed up for my class right now and you need some assistance, you can easily just text me, email me, whatever you need to answer questions. I have no problem with that. Okay, so let's get started. We're going to talk about 4 ways to represent a function. So first, let's talk about what a function does, or what it looks like. A function happens when one value depends on another. Okay? One value depends on another. For an example, the area of a circle depends on the radius. Human population depends on how much time goes by. I know there are other things that could be confounded variables, but we're going to look at this particular one. Cost of mailing a package can depend on the weight. So those are examples of functions. Now some definitions. And yes, you can expect I'll be asking you about definitions. First of all, a function is a rule that assigns each element in X, or in the input set, to exactly one element called f of X or Y in the output set. I would pause this and write this down. A function is a rule that assigns each element X in an input set to exactly one element called f of X or Y in the output set. So let's take a look at domain and range. We're going to be talking a lot about domain and range in this section. A domain, those are generally your X values. Now they don't have to be called X, they can be called any variable you want. But generally, they're your X values. They're also known as your input values. Domain values are the independent variables, so they're the control. They're the ones that control everything. Now, your range, usually your f of X or your Y values, also known as your output values. Range values are dependent variables because they depend on the independent variable, which is a domain. Okay, so 3 really important definitions here. Now, some notes. Let's talk about what a function is like. Sorry about my little water dots on here. I have cold water next to me. A function is like a machine. Okay, you put something in, you do some kind of action, and you get something else out. So that's a function. 4 ways to represent functions, which is the title of this section. Verbally, I can describe a function with words. Numerically, I may give you a table or 2 sets of values. Visually, maybe by using a graph. Algebraically, by using an equation or a formula. Okay? So 4 ways to represent functions. Now we're going to look at a couple examples, and I'm going to go to the book because I think it's better illustrated with their pictures. I'm not the greatest artist. So example 1, the function f is shown in figure 6. So here we have it right here in figure 6. We can see just upon inspection that this function begins on the X at 0 and it travels 1, 2, 3, 4, 5, 6, 7. So it goes from 0 to 7. Okay, if we look at the Y values, we can see that it doesn't go any lower than -2 and it doesn't go any higher than 4. Okay, so what are our questions? Find the values of f of 1 and f of 5. The 1 is your X value. So we will go over here to our graph. We'll look at our 1, go up to find what f of 1 is, and we'll count 1, 2, 3. f of 1 is indeed equal to 3. Okay, and as I say, in other words, the point on the graph that lies above 1 is 3 units above the x-axis. Okay? Same with the 5. If I go to 5, 1, 2, 3, 4, 5. Now I'm going down, but I see I don't have a nice little fit right here. It's not quite down here in the crease. It's a little bit above, so now that requires me just to estimate. And we're big boys and girls now, so we can do that. So let's take a look at this, and we'll say, looks like it's about 0.7 below. 0.7 below the x-axis. So what we're going to estimate f of 5 to be is approximately, that's what this symbol means right here, approximately negative 0.7. The second part of the question asks us, what is the domain and what is the range? Domain, again, are your input values. So what are your input values for this function? Input values mean where are your x values that belong in the function. We already said that it starts at 0 and it travels to 7. So x is going to be greater than or equal to, because it does include 0, there's a solid dot there, and less than or equal to 7. So the domain is a closed interval, which can be written this way, 0, 7. Now notice that f takes on all the values from negative 2 to 4. So we said that before. Our lowest number is negative 2. Our highest number is 4. So that will give us our range. So we can say our y values such that y is greater than or equal to negative 2 and less than or equal to 4. Or we can write it in interval notation, which would be negative 2 to 4 right there. Okay? All right, if you have any questions, just tell me what example your question is in the comment section, and then I'll know which example you're talking about to refer to before we meet. All right, now we're going to go to example 2. Example 2 says sketch the graph and find the domain and range of each function. So here I just have this linear equation right here. Simple 2x minus 1. 2 is the slope, negative 1 is the y-intercept. Here's my graph right here. And they're asking to find the domain and range of each function. So before we go to B, we'll look at A. If I extend my line forever to infinity both ways, either negative infinity or positive infinity, this line will never end. So what that tells me is that my domain are all real numbers. And we use this symbol to say all real numbers. If we're going to put that in interval notation, we would write it negative infinity, oh, it's unbounded, so negative infinity to positive infinity, like this. The second one is a parabola. This is our parent function parabola right here. We want to know what our domain is of our parent function parabola. Like the linear graph, if I extend it forever, my x values will go on forever. So my domain here are also all real numbers. Now range is a different story. Range are your y values. If I go back to my linear and I look at where are my y values here, it also will continue to go on forever and ever and ever, all the way up, all the way down. So my range for this linear function in part A, my range is also all real numbers. However, when I take a look at the parabola that's here, and I'm talking about the range, it doesn't have any values below 0. It's not until we get up to 0 that it starts to have y values. And then it continues on again forever all the way up. So in that case, my range is y such that y is greater than or equal to 0. It does include 0 because my graph includes the 0. If I write that in interval notation, then I will write it like this. I'm going to write the bracket here, 0, because it's included. Infinity is unbounded, as I said before. Infinity always has a parenthesis around it because it does not have an n. And that is example 2. Now I'm going to skip example 3 for a moment and go head over to example 4. Example 4 gives you this graph. Okay? Example 4 gives you a graph, and it says when you turn the hot water faucet on, the temperature of the water depends on how long the water is running. Okay, so here I turn the faucet on. It doesn't start off, you know, I'm looking at hot water here, by the way. It doesn't start off completely hot. It's a little bit cool at first because there's water that's been sitting in the pipe. And it goes up till it reaches its maximum heat value that whatever your hot water heater is set on at your house. So when it comes up and it gets to that height, it stays that way for a while until you start running out of water, and then it starts falling quickly to reach your minimum cold value. So again, we have it starting here, maybe at some lukewarm value. It travels up because we're doing the hot water. It gets to the highest heat level, and then after it starts to run out of water, it quickly drops down to colder. And this is just an example of that itself. Now we know that the domain here is going to be greater than 0 because we're looking at time. We're not going to have negative time. And T is your temperature. I don't have the exact numbers on here to guess what the degrees are as far as the temperature. That's not important for this problem. The concept behind this problem is just for you to understand what this kind of function would look like. We're going to move on to example 6. We'll do example 5 in a little bit also. Example 6 says find the domain of each function. Okay, so here we're looking at domain. Now remember, domain, that's what your input values will be. Okay, so what can I put in to this function and get real numbers? We're not talking about imaginary numbers here. We're looking at real numbers only. So if I take a look at this, I can see that if I put a -2 in for x, I will get my 0. So I can't put any smaller than -2 in for x. And if you don't remember how to do that quickly, I'll show you. You just take whatever's on the inside. Hopefully you can see because I'm going to use a pencil here. We don't want it to be any lower than 0. Okay, so we solve and we see x is -2. Okay, we want this to be actually greater than or equal to 0. So that then will give us our domain. X is greater than or equal to -2. Once again, you can write it in interval notation as -2, infinity. Now part B, I take a look at this. Right away I should look and say, well, it's a rational function. A rational function means whatever is on the bottom cannot be 0. So whatever is on the bottom cannot be 0. I need to figure that out. I'm going to jump over to this next page. Here we have our function. If I factor the bottom of it, I take out an x. I get x times x minus 1. We know that neither one of these can be 0. So I say x cannot equal 0 and x minus 1 cannot equal 0. So if I solve this, I see that x cannot equal 1. So my domain can be all x such that, this little line is such that, it's used a lot, so it's good to know. All x such that x cannot equal 0, x cannot equal 1. Okay? Now you could write this in interval notation. Again, unbounded infinity is a parenthesis. So we have negative infinity to 0. Then I can include from 0 to 1. And then jump over to greater than 1 to infinity. So again, 0, 1 are not included. That's why we have the parentheses here. Now you might say, well, which way do I write it? Well, whatever way you're asked to write it. And if I ask for interval notation, you'll put it in interval notation. If I ask for it in set notation, you'll put it in set notation. If I don't ask, then you can pick whichever one you want. Okay, while we are right here, we might as well look at the vertical line test. The vertical line test is a nice way to check to see if we have a function. If we have the graph given to us, and somebody asks, is this a function? All we have to do is take a look and say, if I were to draw vertical lines through this graph, is there anywhere that would hit more than once? If the answer to that question is no, then it's a function. So this is good. It's a function. Now if we take a look at this second function over here, it comes up, down, and then it turns back around. We can see that if I do my vertical line check, when I get to here and over to here, except for this very end, I'm going to hit it in more than one place. If it is in more than one place, then it is not a function. Again, if it is in more than one place, then it is not a function. Alright, I'm going to go back and look at example 4. I think we're going to start at example 3. Alright, now let's do some math. So here we have example 3. Example 3 gives us a function 2x squared minus 5x plus 1. And it tells us to evaluate this expression f of a plus h minus f of a over h. Now the first thing that I notice is that there are no x's here, and this has x's. Well, it's telling us to substitute a plus h in for those x values, and over here a for those x values. So I like to do that first. If I have f of a plus h, and I'm substituting in a plus h for x, I will have 2 times a plus h quantity squared minus 5 times a plus h plus 1. Now this is a binomial square. You'll hear me say this a lot during this class. You should know how to multiply out a binomial square quickly. Whenever you have this parentheses and the whole thing is squared, you square the first element, you square the last element, then you multiply the two together and you double it. This last sign is always positive, and the first sign is whatever this sign is right here. Okay, so I'll say that again. Square the first, square the last, multiply them together, and double it. This is always positive, and this is always whatever this sign is here. Now, I can't forget my 2 out front. I'll distribute that through in a moment. Oh, I guess I could distribute it through now. Okay, let's go ahead and do it. 2a squared plus 4AH plus 2H squared. And now I'm going to move over here and distribute my negative 5. So I have minus 5A minus 5H, and then of course I have my plus 1. Now I would love for some of that to combine, but I don't see anything that does. So I'm going to move on to the second part of my expression and find out what f of a is. F of a, 2a squared minus 5a plus 1. I just took my function here. Wherever there was an x, I replaced it with the a. Now that I have these two, I can go ahead back up and put it into this expression. I'm going to take the first part, the first one, minus the second one. So that would be 2a squared plus 4ah plus 2h squared. Notice I'm writing a little smaller because I know I'm going to have a long expression. Minus 5a minus 5h plus 1. That's only the first part, right here. Then I'm going to subtract, so I have to remember to distribute the negative. I'm going to subtract this second f of a. So it's going to be now the opposite signs. Minus 2a squared plus 5a minus 1. Now, I want to see if any of that combines before I put it all over h. So I notice here that my 2a squared and my negative 2a squared cancel. Cancel is when you get 0. Then I also notice that I have a positive 1 and a negative 1 and a negative 5a and a positive 5a. So all of that is gone. So what I have left would be 4ah plus 2h squared minus 5h. Now all of that is over the h on the bottom, and remember h cannot equal 0 because it's on the bottom of the fraction. So I have h here. Now, can I do anything else with that? Well, you should notice that we have all h's here and an h down here. So that means I could factor an h out. So let's do that. Let's factor an h out. And that would give me 4a plus 2h minus 5. All over h. Now that I have this, I can reduce. Please don't say cancel, because this is not canceling. This reduces to the number 1, okay? This will reduce and leave me with 4a plus 2h minus 5. Now that might have seemed a little bit unnecessary to you, but there's a reason behind us doing this. This is going to help us later when we define derivatives. Okay? So this would be your answer to your expression, 4a plus 2h minus 5. Okay? Alright, let's go on. We already did number 4 in the book. Let's take a look at number 5. Again, if you have any questions in example 3, you can put in the comment section example 3 and write your question. Example 5 says we have a rectangular storage container with an open top, so we don't have any top on it. It has a volume of 10 cubic meters, so it gives us the volume. 10 cubic meters. The length of the base is twice the width. So if I have my width here, make that W, the length is twice the width. I know my drawing may not look like it, but like I told you, I'm not an artist. And we'll just say H is going to be the height. So we have no idea what the height will be. Alright. Now our question is, the material for the base costs $10 a square meter. So the base only costs $10 a square meter. So we need to write that down. Base cost $10 a square meter. Material for the sides costs $6 a square meter. So the sides are a little cheaper. They're $6 a square meter. Now, let's solve this and see if we can figure out what our dimensions need to be. Okay. We want to write our expressions for our cost function. Here we have to think about how many sides we have in this box. 1, 2, and in the back 3, and then 4, right? So we have 4 of those sides. Now, they're not all the same because this is twice the length of the width. So if I were to find the area right here, that would just be W times H. If I were to find the area here, that would be 2W times H, because area is multiplying the length times the width. Now, how many sides do I have that is as big as this right here? I have 2 of them. So I have 2 times 2W plus H. Or times H, sorry. And then here I also have 2. I have 1 here and I have 1 on the other side. So I have 2 times WH. And that would give me my sides. What about the area of my base? The area of my base would be 2W times W. And I only have 1 of those because it doesn't have a top. So when I simplify that, that'll be 4WH, 2WH, and 2W squared. Now before I go combining anything, let's take a look at what the cost function says it will be. And my cost values for the sides, the material is going to be $6 a square meter. So I'm going to multiply this one by $6 a square meter. This is also a side, and there are 2 of them, so I'm also going to multiply it by 6. The base, on the other hand, is more expensive. It's $10, so that would be 10 times my 2W squared. So here I have, when I simplify, my cost function will be 24WH plus 12WH plus 20W squared. What else do we know about this rectangular box? They told us that the volume is 10 meters cubed. Well, volume is length times width times your height in a rectangular prism, and that's what we have here. So our volume here would be length, width, and height. Length is 2W, width is W, and height is h. And they tell us that that volume is equal to 10 meters cubed. So if I were to simplify that, I would have this. Oh, sorry. I don't want that in there. That's our meters cubed. That's our measurement. We don't need that for now. Okay, and then if I simplify it a little further, we have W squared H equals 5. Now let's see what they want us to do in the rest of number 5. They want us to express the cost of the materials of the function of the width of the base. Okay, so they want us to use the width only to express it. Right now we have too many variables. We have a W squared H, well, we have a W and H, and we have a cost. So we want to just make it a cost function. We have to get rid of the H. How do we get rid of the H? Well, we're going to substitute. So if I solve this for H by dividing both sides by W squared, I will have H equals 5 over W squared. Now how that helps is I'm going to go back to my cost function, and wherever I see an H, I'm going to put that in. Let me move this up a little bit. Here I have my cost function, 24W, here's an H, so we're going to put in 5 over W squared plus 12W, another H, 5 over W squared plus 20W squared. I'm going to simplify that. I'm going to reduce here, and I'm going to reduce here. So now I have my cost function, 24 times 5, 120 over W plus 12 times 5 is 60 over W plus 20 W squared. Now the nice thing about this is they're both over W, so I can combine them. And this would be expressing my cost function in terms of the width of my box. Okay, so before we move on to our next example, we want to take a look at this too and write down any restrictions we might have. And we see here that we have W on the bottom, so we know it cannot equal 0. But if we think logically, we know that W also cannot be a negative number because it's width. So I'm going to have to put W is greater than 0 as my restriction. Again, we're used to putting W cannot equal 0, but you have to look at the context of the problem. The context of the problem is that it's width. So we're not going to have a negative width. So I put W is greater than 0. Okay, now we're going to go back to the book. Going to look at example 7, defining a piecewise function. Now a piecewise function is exactly that. It's broken into pieces. So for one part of the domain, it follows one expression, and for another part of the domain, it follows another expression. So in this piecewise function, I have x is less than or equal to -1. So for the domain that's less than -1, it's going to be a simple linear equation. For x is greater than -1, it's going to be a parabola. So let's take a look at that graph I have right here. Okay, so before -1, I have this linear graph, which is 1 minus x. You can see that it has a downslope. That's where we get our -x. And if we continued on down through, it would hit the graph at 1. That would be our y-intercept. But we only take it to here because that's where it's defined. And it's a solid point because it's included right here. The -1 is included for this expression. So that's why we have the solid circle. Now the parabola begins after that. The parabola begins greater than -1. So that's why we have an open circle. I hope you can see that right here. That's an open circle because it's not included. Now our question says evaluate f of -2, f of -1, and f of 0. F of -2, you need to go up here to the domains and say, which one am I going to use? Well, -2 is smaller than -1. So I'm going to use this part of my expression, put -2 into that part of the expression, and I get 1 minus -2. Minus negative is positive, and that'll equal 3. Again, since -2 is smaller than -1, I put -2 in here, and I get 1 minus -2, and that will give me 3. The second one says, what about f at -1? Well, f at -1 is still in this part right here. So if I want to put -1 into my expression, I put 1 minus -1. Minus a negative will equal positive, and I get 2. Now I can see here by my graph that that makes sense, that this would be at 2. Considering the distance right here to here at 1, this would be 2. The last part of this example asks for f of 0. Well, 0 is bigger than -1. 0 degrees is warmer than -1 degrees. Not much, but it is. So I'm going to use this expression. I put 0 into this expression, and 0 times 0 is 0. So f of 0 is also equal to 0. Okay, as always, if you have a question, you can put it in the comment section, or you can text or send me an email if you're in my class right now. All right, next example is example 8. Example 8. Sketch the graph of an absolute value function. Well, hopefully you remember from your graphs that this is a parent function of the absolute value function. It's also a piecewise function. The definition of an absolute value graph is if x is bigger than 0, then you're just going to graph y equals x. That's right here. But as soon as x is less than 0, then you're going to take the opposite of it. So for instance, x is -1, negative of -1 is a positive 1, and it reflects it back up above the x-axis. So this is an example of using a piecewise function. Example 9. Example 9 wants you to find the formula for this graph. Well, let's take a look at what we know. I can see that we have a point right here at 0, 0, and I can see that we have a point right here at 1, 1. if I use those 2 points to find slope, I would get the slope of 1. I also see that my y-intercept is 0, so b is equal to 0. So knowing that, I can see that this first part of the equation is going to be y equals x. So from 0 to 1, it's going to be x. Then what happens is it comes back down negative. It is also a slope of 1, but this time negative 1. And it stops doing that at 2. So from 1, but bigger than 1, to 2, and including 2, my line, and I'll get a pencil here and draw it so you can see a little better. If I extended my line, this linear equation goes through the y-intercept at 2, would be 2 minus x, because negative 1 is the slope. So 2 is my y-intercept, and negative 1 is my slope. So just from here to here, though, is 2 minus x. After that, it just flat lines and stays at 0. So anything that is bigger than 2, the answer is just going to be 0. So this is an example of how you can develop a piecewise function. You look at the pattern, it's going up, and now it's changing. Once it changes, that's a different piece. Now it comes down, and then it changes again. Once it changes, it's a different piece. Okay. Example 10, another piecewise function. It's an example that's commonly used. We say this is the cost function of mailing a large envelope. If this is from 0 to 1 pound, and including 1 pound, you're charged 88 cents. As soon as it goes over 1 pound, up to and including 2 pounds, you get charged $1.05. Bigger than or equal to, or I'm sorry, not equal to, bigger than 2 and less than or equal to 3 is $1.22, etc. So what does this look like? Over here, this is a step function. Looks like steps. From here to here, we have 88 cents. Now, we're not going to have a way to 0, so it's an open circle. So open circle, 2 over and including 1, so that's closed circle. Once we get bigger than 1, it jumps up to the next cost. It stays that cost until we get to more than 2. It includes 2. As soon as we get more than 2, it jumps up. And then it moves over and stays at this cost, which is $1.22, until it gets more than 3, and then it will jump again to $1.39, and it goes on, etc. So this is an example of a step function. I know this is a long section, but that's how first sections of the book always go, because they throw a whole bunch of material at you that should be reviewed. So hopefully, as I'm going through this, you're saying, oh yeah, I remember that. We're going to talk a little bit about symmetry and even and odd functions, just for a review again. Now symmetry looks like this. This is symmetric. I can draw a line through it, and I have mirror images on each side. This is an even function. How do I know it's an even function? If I put in a negative value into the function, and my function here is x squared, I square that, and I get f of x. So I have f of x equaling x squared. if I put a negative value in there, I still get what I had before, f of x. When that happens, that causes symmetry. We call that an even function. So a graph that looks like this is an even function when it has symmetry. If it is an odd function, when I put the negative x value in, I'm actually going to get the negative range value. This is called an odd function. So if I put a negative value in, like my cube right here, f of x equals x cubed, it comes out negative. That is an odd function. Let's look at 3 quick examples. Here I have f of x equals x to the 5th plus x to the 1st. Now you're going to find out that both of these exponents are odd, and that's going to be no accident. When I check to see if it is an odd function and I put negative x in, if it is an odd exponent, I'm going to get a negative value. So I get negative x. So this indeed is an odd function. Likewise, my next one is to the 4th power. That's an even number. Whenever I take a negative to an even power, it becomes positive. So what I started with here is 1 minus x to the 4th. When I put negative x into the function, I still get 1 minus x to the 4th. Since that is the case, this is an even function. Now notice this next one has an odd exponent and an even exponent in it. And to no surprise, when I put my negative value in, I don't get the positive of what I had, and I don't get the negative of what I have. I have a mix. When I have a mix here and it's not completely the same or completely opposite, it is neither even nor odd. Neither even nor odd. Okay, lastly, very last thing, can you believe it? Last thing in this section, we're going to look at increasing and decreasing functions. This definition seems a lot more complicated than it has to be. This basically says if a point before another point is smaller, then you have to be increasing. In other words, let's say this point right here is 4. And let's say the point next to it is 6. Well, 4 is going to be smaller than 6. So if you go from a smaller number to a bigger number, then you know you're increasing. That's all that means. If you go from a, we'll say over here now, we'll make this x sub 3 and x sub 4. We'll say x sub 3 is here and 4 is here. So this, we're going to say that this value, and I'm just making up numbers here, but I'm going to say this is 7, and I'm going to say this value is 5. So my x sub 3 value is 7. My x sub 4 value, if I come across, is 5. Whenever this happens and my first value is bigger than my second value, then it's going to be decreasing. And believe it or not, that is all of Section 1.1. I know it's a lot of information. The first class always has a lot of information, but I would suggest that you just go back and you review this video a couple of times, because it'll give you a good base for the remainder of the class. So, next video will be Section 1-2. I'll talk to you guys soon, and I say peace out.